Excellent. So, hello and welcome. As usual, a couple of announcements. First, yes, this is the last week. Yes, the homework you're turning in today is the last homework. We will have a short lab on Thursday as well as the last quiz. Any questions about that?
When will the lab be due?
I'm going to try to make it due so that I've got time to grade it, let's say Saturday. Okay?
Okay, that's fine.
Okay, cool. And as far as the quiz, the next Friday as usual. Yes, I know there's a couple of people that have scheduling issues, and I will see to that. As far as the grades, if you look in the grade book right now, the current things that are blanks are basically the rest of the stuff till the end of the year. So some of those things that are blank you haven't taken yet. Any questions?
No, I don't think so.
Excellent.
I sent you my homework this morning. Did you get my homework from this morning?
Yes. Yes,
It
I
would have
did.
been in your email.
Yes, I did. Okay, then. With that said, then the other thing that I wanted to... Good.
And all my email. Oh, I was just saying I've sent all my homework through email. So if I'm missing any homework, okay, all right. I just want to make sure I wasn't missing it.
I think I may have been missing a page from the last homework, but I did get the majority of it.
Okay.
Yep.
From the last.
Yep.
I'll take a look and I'll see if maybe I missed a page or something.
Okay, cool. Anything else then?
I'm good.
No. Then, as usual, because we have a homework today, let's make sure that we all know how to do those problems. So, do we have any problems that we'd like to basically go over?
Can we go over someone else saying something?
I was going to say, can you go over chapter 14, number 12 on the review problems?
Actually, that works for me too.
Okay, just a second. Let me flip to that page. 12, you said, correct?
Yeah,
Correct.
I think he said 12.
Okay, then. Oh, I lost page just a second. Just gonna walk over. Just a second. Here we go. Number 12 says a 161 kilogram steam boiler is made of steel and contains 1,127 newtons of water. It's a little bit awkward that they chose to measure in newtons, but we'll fix that. At 8.9 Celsius. How much heat is required to raise the temperature of both the boiler and the water to 100 degrees Celsius? Oh, okay. So,
Can you move the board a little bit closer?
here's what's going on. We've got two objects, okay? And they're both heating up. And so we know that Q equals mc delta T, okay? But here's the thing. We've got two objects, right? So we're going to have two masses, two specific heats. And because they're in thermal contact at the start and thermal contact at the end, we're actually going to have the same temperature change for both. But basically, we can write this as having it twice. Where this is for the boiler, and this is for the water. Okay. Cool. Well, then the first thing that we're going to do is they gave us the mass of the water in newtons for, I don't know what reason, but that's what they did.
Hey, David,
Thankfully, it's easy to switch. Go ahead. What's up?
what is the sign in between those two?
The plus.
Okay, thank you.
Can you move the board a little bit closer?
A little bit, yeah.
Okay.
How about here?
Oh yeah, that's good.
Is this better for lighting then?
It's kind of blocking out the C a little bit on top up there, but
Blocking out C is the light bulb that's up there.
okay,
Sorry, I can't help that.
that's fine. I can still read it.
Anyhow, where was I? Oh yes, switching the water mass. So that's just going to be the force that they gave in newtons divided by G is equal to our mass for water. That's equal to what is 1127 divided by 9.81. Throwing that into the calculator real quick. Very good. There we go. I'm just going to round that up. That's fine. 115 kilograms. Okay. So we have 115 kilograms for our water. We have 161 kilograms, for our mass of the boiler. Now, the next part we're going to have to look up, okay? We're going to have to look up the specific heat of water, and we're going to have to look up the specific heat of steel. Thankfully, there's a nice little table in your book on page, let me find it. It's little conductivity, sorry. Here we go. But did they not give you a table?
I think there is a table
That's
at
a
the
bit
back.
of a nuisance. Okay, so that means that they have it in two different examples. So, copper, steel. So it says the specific heat of steel is
I think there might be one at the back of the book.
0.115 calories per degree C and 1 calorie per degree C. Now, the bad news there is that it's in calories. The good news is that 1 calorie is the amount of energy that it takes to heat up water by 1 degree. That's why it's 1 to 1 here. And I just do have, I can just look up waters to make sure that I get it right. I'm pretty sure it's 4.8. Oh, I'm sorry, 4.2. 4.18 is what I was thinking. So that means that this is actually not going to be in calories. It's 4.18, and we have kilograms. So I'm actually going to make that 1,000. Here, what I want to do is I want to basically multiply by this number. So 0.115 times 4180. I got that this is now 480, I'll just call it 481. Okay, so we have our M's, we have our C's. Let's find delta T. Well, it said that they both start at
We'll start at 8.9 degrees at 8.9
yes,
degrees Celsius.
8.9 degrees Celsius. And they end at 100, so 100 minus 8.9 equals delta T equals, that's just going to be 90.1, right? Yeah, oh, 71. Okay, so at that point, we have all of our variables. Just throw them into the calculator, get out an answer. So Q equals 61 times 481 times 91.1 plus 115 times 4080 times 91.1. I got 5.08 times 10 to the 7th joules. Now, the fact that this is such a large number is why some books prefer to use the calories that I was talking about, but it's just adding an extra unit that we don't need, and so I chose to move on past that. Any other questions about this problem?
I don't think so.
Excellent. I apologize that they hid the specific heats for you in an example. Any other problems that you'd like me to go over?
Yes, could you go over chapter 14, review problem number 14?
Number 14, okay. So 355 gram piece of metal at 48 degrees Celsius is dropped into 101 grams of water at 15 degrees Celsius. If the final temperature of the mixture is 32.5 degrees Celsius, what is the specific heat of the metal? Okay, so that's going to be a similar thing here, but what's going on is that we're using the method of mixtures. So that's the thing that I've shown you guys a couple of times. Where we said that whatever heat the metal loses is the heat the water gains, okay? And so we get that negative M for metal, C M for metal, delta T M equals positive and W, C W, delta T W, okay? Now, this is the one that I said always use Kelvin to basically make sure you don't make any mistakes, because it's very easy to make mistakes if, when you have that negative sign in there. So I will convert things to Kelvin if you feel that it would be easier just to leave it in degrees Celsius. For this particular problem, that would be fine. Anyhow, with that said, we know the masses, but we're looking for the specific heat of the metal this time. That's what we don't know, okay? We know the mass of the metal is 355 grams. We know the mass of the water is 111 grams. We still know that CW is 4.18, okay? And we can find delta T W and delta Tn, okay? So what's going on is, again, the metal is losing temperature and losing heat. The water is gaining temperature and gaining heat. So, as always, delta T is Tf minus Ti, it's T final minus T initial. For the metal, it's going to be 48 is initial, 32.5 is final.
Hey, David.
It goes backwards. What's up?
What is MW? I can't read that. Is that 111?
Mass of the water, 111
Yeah,
grams.
mass of water.
Yeah, 111 grams. That's 48 grams, correct? Yes. 48. So this right here, because it doesn't end up causing any problems, all your numbers are positive, is why I said that you can stay in Celsius. What I'm going to do is just convert this all to Kelvin real quick, because I said just always do Kelvin. So 273, 1, 1 point 5 minus wait, did I do that wrong? Just a second. 32. So yes, I did. 0, 5. 48. So 273 plus 48. So 273 plus 50. Okay, so that should be it in Kelvin. Same over here. Our final temperature is still 305.5 minus the initial temperature of, so 15, 8, 288. Okay, I'll just write it below, minus 288. Okay. Now, at this point, I can do some simplification with these, but what we're really looking for again is CM, right? And so what I can really do is I can divide both sides by these two multiplied together, okay? Now I'll leave CM on one side by itself. Don't forget to also divide by the negative. Okay, so with that done, at this point, all it is once again, taking this, plugging into the calculator, to get your answer. Did I make a mistake? Yep. Okay, just a second. That number makes a lot more sense. I got that Cm equals 1.47 joules per gram Kelvin. Okay, any questions left about this problem?
Nope, I'm good.
Cool. Any other problems you'd like me to go over?
Yes, can we go over on chapter 14, the applied concepts number 3?
Okay, is this, then we'll start that one. Okay, so number 3 says, what is the heat of fusion for water in problem 2? Okay, so basically I'll just read off problem 2. Problem 2 is really short, that's why I didn't assign it. It just has a lot of words. Every winter, a local recreation department fills a parking lot with water, so the water will freeze and people can ice skate on it. Although the weather does not get cold enough for the water to freeze, the water temperature drops from 4.3 degrees Celsius to 0 degrees Celsius. If the water is 12.7 centimeters deep and the parking lot is 24.5 by 33.8 meters, how much energy does the water release into the air? Okay, so that was 2, and I didn't assign that one. Number 3, however, asks for what is the heat of fusion for the water in that pool to now actually freeze into the solid block of ice. Okay, so the trick goes like this: Q equals mL. For now, we have to look up L. That is my heat of fusion. Okay, and that's just a specific value for water. Okay, so just looking that up real quick. Okay, so this is saying that it is approximately 334 joules per gram. Okay, so L is 334 joules per gram Kelvin. Note gram specifically, okay, because that's going to be a bit of an issue in the next step. Now, the next step is going to be that, wait, we know how much water is there, okay? They took this giant box, basically, and filled it with water. And we know what the density of water is. The density of water is 1 gram per cubic centimeter, but that's unfortunately kind of small for what we are dealing with. What we really want is that it's thousand kilograms per meter cubed, which is something that you guys used a bunch of times on another chapter where you were dealing with the fluids and what the density of water was, right? So with that said, we can then take the volume of this box, which it said that it is 24.5 by
33.8.
33.8 by 0.127. Okay? Those are the dimensions of a box. And actually, one thing that I'm going to do real quick is I'm going to convert this to grams, because we said that's the specific heat of fusion rather in grams. So instead of 1,000, it is now 1 million. I multiply those together, I get that the volume is 105.17 liters cubed. Okay, that gives me a mass of 1 million times 105 times 5.17. We're just going to write that as 105.10517 times 10 to the 8 grams. There's a lot of water. Okay, as you might expect, it's a ice skating rink, right? Then, in order to figure out how much heat it actually takes to freeze this thing, we multiply by another 334. So we take this number and plug it in here. This number goes here, okay? Such that Q to freeze that water is then 3.512 times 10 to the 10 joules. That is a lot, okay? But we're not actually done. That was A. B just builds on this. B actually asks you to do problem 2 and then add it to this, because the total energy, the total heat to reduce the temperature and then freeze it is simply going to be Q equals M times C times delta T plus ML. Well, the good news is we already know ML. We found that A. So we just need to do this. We already know M. We already know C. That's our 4.18 rather. And delta T, well, we know that it ends at 0. So it's just going to be negative, where did it start? 4.3. Okay, and M is this again. Okay, cool. So I plug those 3 in, add it to this. It's going to be a very small addition compared to this. Oops, not divided, times. Oh, I apologize. There's one thing that I should have mentioned. We are freezing the water, and so it is losing energy. This should be negative. That's why I said that we're going to basically be adding. Okay, that makes it all work again. So, add that in, you get that Q total. So this was A. B, Q total, which comes from this, is 3.702 times 10 to the 10 joules. Joules.
Hey, David.
Yep.
I had my, I don't know why, for some reason I had my answer, or my M in kilograms.
Okay. So what you do is you take your 4.18, multiply it by 1,000, and you take your 334, multiply it by 1,000.
So my answer for A, I got 8.4 times 10 to the 6 K cal. Is that any
Oh,
work?
you're in calories. That would do it. Okay.
Should I just change it over?
Yeah, you can convert.
Okay.
To go from calories to joules, we talked about that one earlier.
Okay, thank you.
Cool. Any other questions?
On this one or?
Yeah, just a second. Let me make sure that I did all the parts.
There's a part.
Oh, nope,
There's
there is a
part
part
C.
C. Okay, so part C, all that you do is it just changes delta T here, okay, to make the number bigger. Now you have your final temperature is a negative value. This is where I'm going to say, hey, let's make sure that we're working in Kelvin to make sure that we don't get anything all mixed up. Okay, so once again, same equation. Part C, delta T is going to be equal to TF, so 273 minus, where do we go? 273 minus 3.43, that's going to be 269.5 something. Yep, 269.57 is my final. And the initial of 4.3, so add 273. I get 277.3. Okay. Do those. We get that delta T for part C is now negative 7.73. Okay. Then all you do is you just take that, plug it back into this equation again, and answer it. So 3 plus that one plus, and we get that Q equals 3.85. We'll just leave it there. Times 10. No, I'll go another decimal place because I did it over 5.2 times 10 to the 10 joules. Okay, there's part C. Any other questions?
Can we, one more question, I think. It's on,
Then, just to keep your life simple, do delta C and delta T in Kelvin, such that delta T is always TF minus TI.
okay.
Okay. I'll do one more problem maybe, and then I really do need to move on to waves again.
Okay, can we do, chapter 15, number 12?
Chapter 15, number 12. Okay, an ideal gas occupies a volume of 4.5 liters at standard temperature and pressure. What is the gauge pressure in kilopascals if the volume is halved and the absolute temperature is doubled? Ooh, there's a lot of vocabulary words there. Okay, so standard temperature and pressure. What is it? 0 degrees Celsius, so 273 degrees Kelvin. That's the temperature. The pressure is 1 atmosphere, okay? It's the standard lab conditions, okay? With that said, let me erase this because the next thing that we're going to do is we're going to change some values. Where did I put that eraser? Okay. Just blends in with all the other black stuff. Okay, so we have that. .5 L at STP. Okay. But we're going to cut the volume in half. Okay. And we are going to double the absolute temperature. Okay. Well then, what we're going to use is our ideal gas law. That is to say, E times V equals N R T. Okay? And from there, we're going to say, okay, we know P is 1 atmosphere, but we don't want it in atmospheres. We also know V is 4.5 liters at the start, but again, don't want it in liters. And we know T, and we can leave that one in Kelvin. So the first step is accepting how many pascals is a liter. I just said that wrong. An atmosphere. So I get 1,000, I just said that wrong, 101,325. So P at the start is V, I'll go from liters to cubic meters. So liters, odd. 1 milliliter equals 1 centimeter cubed. There are 1,000,000 centimeters cubed in a cubic meter. Okay? Remember, all around water, so same number of grams is how many cubic centimeters you have. But we don't want cubic meters. We want to go to liters. 1 milliliter is 1/1000th of a liter. So what I want to do is I want to take this and divide by 1,000. Thankfully, that just gets rid of those 3 zeros. Okay, so I take this number, divide by 1,000, and get my cubic meters. Oops. Okay then. So we have our values for our start. What we're actually going to do in order to solve this ends up making it so that we don't need to worry about N and R. So how does that work? The way that that works is the same trick that we talked about when we were going over this in the class at the start, is that we're actually going to set this up as a ratio, okay? Where we have P1 times V1 equals N1 times R1. Well, R is a constant, it's going to stay the same, so I'm just going to remove the 1. Times T1, all of it divided by P2 times V2 equals N2 times R times T2. Okay? Well, the number of particles didn't change, so we're actually just going to make those two ends cancel. R is a constant. I certainly hope it's not changing. Those cancel. Okay? And we're left with P1 times V1 divided by P2 times V2 equals T1 divided by T2. Making sense so far?
Yeah, a little bit.
Okay. Now, that's where I say that we have good news. Okay? Because it actually gave us information about V2 and T2 as well. Okay? T1, we now know, is 1,100, rather 101,325 VA. We know V1, I just found it for you. But I'm going to tell you that it doesn't really matter that much. We also know T1. Okay? Why do these two values not matter that much? Because what's going to actually happen here is we said that we're cutting this in half and we're doubling this. So this ends up being 2 times 273. And hey, look, we got a 273 here, 273 here, this one cancels. This ends up being 0.0045 divided by 2. And hey, look, we got 0.0045 here, and 0.0045 here, and up they cancel. Okay? Such that what we really have left at the end is
Is that 101.325, or is that?
Yeah.
Okay.
oh, that's something I can solve, right? That's after I basically eliminated all these other values that I was talking about that we can get rid of. Is this making sense now?
Yeah.
Okay. So first thing I'm going to do is I'm going to get this half on the bottom, multiply it to the other side. This half and this half to cancel. Okay?
Okay.
Which leaves me with because anything times 1 is itself. Which means that P2 is the same value that I started with. And to put that into kilopascals, put a decimal point here and call it kPa. Questions? Yes, that change in temperature and change in volume just canceled each other out, such that I get the same final pressure. But I went through the long way to show you how to find that.
Okay. And is this say 101 point? That's okay. That's 101 point.
Yeah.
325.
Because we went,
Okay.
this is in Pascal, and so to get to kilopascal, I just divided by 1,000.
Okay.
Okay. Any other questions? Then if you have more problems that you want me to go over, I will have to go over them Thursday. Let's talk a little bit more about waves, okay? Because the last one is going to be about waves. So let me erase this. Now, when we left off last time, we were talking about standing waves, and we were talking about the equation to figure out how many standing waves I can fit on a string or in a pipe like a flute, etc. Okay, and what we had stumbled across was the idea of nodes and harmonics. Okay, so let's just basically pick up with what is a node, what is a harmonic, and what are my conditions. So we said that. Okay. I've got a string, right? And I send the wave in, okay? And it hits the wall, bounces back. This is going to be flipped, so. And they're coming at each other. Because I keep on adding in more waves, well, when these two collide, they're going to completely cancel out at first, right? Because this bump's going to cancel this bump. This one's going to cancel this one, right?
Mm-hmm.
But what about once they get past each other? Well, the thing is, behind this, it's going to bump like this, right? And so once this gets past this, it's this one, right? This adds to this one, and it gets bigger. This adds to this one, and it gets bigger. I get amplification. And then it cancels out again. And then they add again. And then it cancels out again. And they add again. Such that in the end, on this string, I get something that looks like I drew that center point poorly, but I get something that looks like this. It keeps on alternating back and forth between canceling out and completely amplifying, okay? Something that looks like this, where it basically alters back and forth between canceling out and amplifying, is the optical illusion that we call a standing wave, okay? The wave is not actually standing still. I just have two waves continuously interfering with each other such that it looks like nothing is moving, okay? Such that it looks like it's just the amplitude constantly changing. Questions so far?
No, I think I'm good.
Cool. This point right here that doesn't move, that basically is just sitting still as the string around it moves up and down and up and down. That point right there we call a node, okay? Now, what am I talking about by harmonics? It turns out that we can pull off this trick, this optical illusion, only in specific cases, okay? If I have full wave, I drew that somewhat poorly, a full wave on my string, that'll work, as we just described with our original drawing. If I have, say, 1 1/4, not so much. Why? Well, because what happens is this, okay, quarter tries to cancel with this half wave, and they don't actually completely cancel out. You got another half of that half wave, right?
Yeah.
Look at this jumble of different interference patterns moving down the string that just ends up being almost chaotic, okay? Only when I have 1/2 a wave, 1 wave, one and a half waves, 2 waves, etc. on my string does this work. In other words, I actually need to go up by intervals of a half wave each time in order to keep this working. Okay? Anything other than intervals of a half wave, and I get that mixed jumble that just does not come out pretty. Any questions so far?
So to be able to
Okay.
Good.
Then each time we increase how much of a wave we have on the string, we call it a higher harmonic, okay? Where it actually works out that with 0 here, or rather 1/2 wave here, we give it a number 0 for its harmonic number, and we call it the natural frequency. The pattern that you'll get is just something like this, where it's vibrating up and down and up and down and up and down, okay? If I fit another half wave such that I have the full wave in, I'm not drawing the best tonight, sorry. We call it the first harmonic, okay? It has 1 note. If I add another one, we call it the second harmonic, n equals 2, and it has 2 notes. And the pattern just continues. Okay, well, because it's a nice pattern, I can actually write an equation to describe this pattern and figure out what the wavelength of any given harmonic for a specific string should be. If the length of the string is L, okay, then L equals n plus 1, because I have to deal with that 0, divided by 2 times lambda, okay? So if I plug in n equals 0 to find my natural frequency, 0 plus 1 is 1, I get 1/2 my wavelength is L. Yeah, that matches, right? If I plug in n is 1 for my first harmonic, right? I get 1 plus 1 is 2, 2 divided by 2 is 1, 1 full wavelength is the length of the string. Making sense so far?
Repeat that last part again.
Yeah. So I said that if I plug in 1 for my first harmonic,
Okay.
1 plus 1 is 1.
1 plus 1 is 2.
2. 1 plus 1 is 2. 2 divided by 2 is 1 is where I was going with that. Okay. And so 1, right, times lambda. Lambda is L. I have 1 full wavelength is the length of my string. Making sense?
Okay.
Okay. Cool. But that's one of the possible conditions. Okay. That's if I have both ends are fixed. Or I've got something vibrating it on this end. Okay. This end is effectively fixed. And this end is fixed as well. Okay. You see this sort of set up with things like string instruments, the guitar, piano, the violin, etc. What are my other options? Well, we can talk about different instruments. For example, let's talk about the flute. The flute, what happens is you have a pipe. Okay? And the pipe's closed on one end. Okay? I can't get the air at the end of the pipe that's closed to move very much. So that's like having a fixed end, a lot like with the string. Okay? On the other hand, the other side of the pipe is open. Pipe, that's the part you kind of blow into, so it has to be open, right? That's going to be what we end up calling the loose end. Wave's actually going to be kind of optimal for it to be maximum amplitude at those 2 points. Okay? So how can I fit a wave into this? In this case, instead of starting with the half wave, what we do is we start with a quarter of a wave. We'll probably draw this poorly. Okay. And that's our natural frequency. Then we add in a half of a wavelength each time. So for our next harmonic, for our first harmonic, not our natural frequency, we get something that looks like this. I'm going to draw my first node. So we do get a node, then we get a quarter of a wavelength again. Okay? For our second harmonic, we have two nodes. So one about here and one about here. I usually would draw this with different colored markers, but you guys said the different colored markers don't show up well on the camera. So here's my second harmonic, n equals 2, where I see that basically I've gone up by half, by a half wavelength each time. Okay?
Okay.
So how does this work? It's basically the same thing. I can, to make it look really similar, I can write it like this. Okay, where I'm still going up by a half wavelength each time, and a half divided by 2 is a quarter. But most textbooks don't write it like that. They don't like to have the 1/2 in the numerator. So a lot of times what you see is this instead. 2 then plus 1 divided by 4. Okay? That's for one fixed end, one open. Cool. But what about something like organ pipe? Okay. Or this might be an oboe instead originally. What about something like, say, an organ pipe or clarinet or something like that, where I've got 2 open ends? Well then, again, I expect these to be maximum amplitude points. And it turns out that I can't draw something that has maximum amplitude points at both sides without a node at the start. Now, it looks kind of weird, but this is a half wave again. If I were to take and split it here and shift this side over to this end, you'd see that half wave pattern that we're already familiar with, okay? So what ends up happening is, this is my natural frequency. I add another node in the middle. And it ends up adding a half wave to get to my first harmonic. I add another node past that. 2, 3. Pardon my poor drawing. Okay, so I'm basically going up by a half wavelength each time again. I started with a half. I get the same equation. Okay, questions about the equations?
I think I'm getting it.
No. Cool. So at this point for waves, we've talked about some really basic stuff with interference. We talked about the fact that waves always move. This standing wave thing is an illusion, right? We talked about how to create standing waves. We talked about what's going on with wave collisions, and which we call interference. We talked about what happens with when they collide with a barrier, which we call reflection, right? So what's left? Well, there's a couple of things left. The first one plays around again with what how we basically define our waves, okay? And what I've been drawing so far are all called transverse waves, where I have some reference point. My wave is moving along the direction of that zero, and my amplitude is perpendicular to the direction that my wave is traveling, okay? The other option is what we call a longitudinal wave, okay? I still have the direction that my wave is traveling. It looks like my black marker is starting to die. I might have to change to one of the colored ones anyhow. Sorry, guys. Anyhow, I still have the direction that my wave is traveling, okay? But the amplitude is changing in the same direction. How do I get that to work? Well, one way to get it to work mechanically, like actually physically, is to have what we call a compression wave, okay? Where I've got forces compressing or stretching out the material. Such that here, say, it's a lot less dense. One of my peaks is going to be more dense, then it becomes less dense, then it becomes more dense, then it becomes less dense, okay? Such that I have changing density as I go along. Does this make sense? Think about a slinky, okay? If I were to take the slinky and have one side fixed to, say, the board, and the other side in my hand, if I wave it up and down, okay, I get my transverse wave.
Okay.
If I have it fixed to the board again and the other side in my hand, and I shake it back and forth forward, right?
Yeah.
Parts of it are going to compress and parts of it are going to stretch out, right?
Yeah.
Shake it back and forth forward, I get my compression wave, my longitudinal wave.
Okay.
Does that make more sense?
Yeah.
Cool. Okay. So why did I introduce these longitudinal waves? Well, it turns out that an excellent example of a longitudinal wave is sound. How does sound work? What is sound? Well, when we'll talk about a speaker, because it's easiest to explain. When a speaker makes sound, what a speaker is, it's generally just a cone, okay? But a cone that can move back and forth, okay? So that what happens is, when it moves forward, it compresses the air in front of it because basically it's pushing that air forward, and the air that's already there doesn't want to go anywhere until it gets pushed. And so it compresses it. And then when it moves backwards, well, then it basically creates a small vacuum temporarily. It's still. It decompresses the air when it moves backwards, okay? And so sound is nothing more than an alternating pattern of compression waves, okay? Any questions about that?
Okay.
So we're already familiar with all types of things with sound, right? Who here knows what I'm talking about by pitch?
Yeah. I kind of know, but
How
maybe
high
refresh.
or deep the sound is? The
Oh, yeah.
it's really
Yep.
deep was is high.
Yeah.
That is tied to the frequency, okay?
So it's kind of been a while since I've
Okay.
did music.
How
So
loud the sound is. I can talk very quiet, such that or I can talk very loud, such that the speaker picks it up just fine. How loud it is tied to the amplitude. So then what determines the speed and what determines the wavelength? Okay, because if I already know the frequency, right, from our equation that V equals F times lambda, right? If I pick one more, I know the other. Well, it turns out that the speed is determined by the material, okay? Okay, so for example, sound has a certain speed in air. It has a different speed when it travels through water. You can still hear things underwater. It has a different speed when it travels through a wall. If you were to put your ear up against a wall, you can hear things through it. Sound has different speeds depending on what material it's traveling through. Does this make sense?
yeah.
And that, along with the frequency, will determine what the wavelength is. Questions?
Nope.
No. Okay, well, we got a problem. These are three things that we're kind of already familiar with. Who here has ever heard of basically the idea that I always want to keep the length of the cord for two speakers? Yeah, I know, this is going back a bit such that we have cords and it's not all just Wi-Fi or Bluetooth. I'm sorry. But who's ever heard of the idea that I want the length of the cord for two speakers to be the same despite where I want, where I'm putting the speaker? I might put one right next to me and the other one on the other side of the room. I still want the cords to have the same length.
Correct.
You know why?
No.
Because sound can also interfere, okay? But one of the things that I haven't really talked a whole lot about is how waves spread and how waves interact across an area instead of just along a line, right? Okay. So a lot of times, in order to explain it, we think of the wave traveling out in nice circular patterns, or actually spherical if we're thinking 3D, but that's kind of hard to draw. So we're going to stick with circular patterns. Okay. What ends up happening is if I have one source of sound here, and I'm sorry guys, I really do have to change markers. This one's dying really quick.
Okay.
I've got a source there. As the wave spreads out, okay, I keep my wavelength, the space between the peaks, the same, okay, as it spreads outwards. Cool, cool. There's something I can talk about with that in a moment. But first, the interference, and the reason why we want to keep the points the same. Well, here's the thing. If I have a second source here, it also puts out waves. Do that further. And everywhere they overlap, I get interference, okay?
Okay.
You see these patterns like this. You can actually watch this sort of pattern here in water if you drop 2 droplets in, okay? That's not too surprising. That just looks like 2 expanding ripples that hit each other, right?
That makes sense, though.
Yeah. Now let's talk a little bit about the thing that's a bit more surprising. What do they look like when they basically reach you or hit a wall or something like that? Okay? You might expect just one continuous pattern, it drops off the further away you are, etc. Right? Unfortunately, that's not true. Get something that looks more like this. Okay? Where you get peaks of a lot of constructive interference because this one is overlapping with this one. It's basically a peak like this, where there are 2 peaks overlap. And you get points of a lot of destructive interference. Okay? Where basically a trough, in the middle of it, hits a peak and they cancel out. Okay? You don't want that. You particularly don't want that being what your speakers produce. Okay, what do I mean? Well, if I had these offset just right, so that whenever this one makes a peak, this one makes a trough, they could basically start to cancel each other out all the time. And so you want to keep it so that they're nice and in sync, right? Such that they amplify and you don't get either screwy interference patterns, garbling the sound, or making this, or destructive interference all the time, making the sound quieter than it should be. Does this make sense?
Yeah.
Also, it can be useful to consider, well, where you want to sit in the room. Generally, you want to sit centrally placed, somewhere like here, where it has the same distance to you between the speakers, okay? Because if you sit, say, over here, then the distance between you and the speakers is different. And here you can see that would be another case like this, right? So the 2 ways that this can change is either I have my 2 generators out of sync, or that I have the distance between my 2 sources out of sync. That'd be different. Does that make sense? Because I can also draw it over here where the differences are distant, where the distances are just different, right? Such that I get this destructive interference. Questions so far?
No, I think I'm good.
So how do I find these points that basically I don't want to see? Well, the key trick is that what I don't want for that destructive interference is I don't want the difference between the distances to be a half wave. I don't want the difference between the distances to be such that I get a peak when I get a trough, okay? So I will get destructive interference when 1/2 lambda, half of a wave, is L1 minus L2, where say this is L1 and this is L2, okay? I will get constructive interference where lambda equals L1 minus L2. Now, the reason why I don't just look at L1 and L2 and look at them in their entirety is that, you know, the wave is going to go through several full wavelengths getting to here. And if they have full wavelengths, we don't really care. So what am I trying to say? If this one travels, say, 1 full wavelength in order to reach you, whereas the other one travels, say, 3.5 full wavelengths. I'm sorry, that's 1.
Hey, David.
Yep.
Just letting you know you got a couple minutes left.
Okay, gotcha. There's 3. Such that it travels 3.5 wavelengths to reach you. I don't care about these wavelengths back here. They don't really matter so much. What matters is that last bit. Does that make sense?
Yeah.
That this one hits a trough and this one hits 0. So the full wavelengths up to you don't matter. That's why I can subtract the 2 of them and just see what the difference is. Make sense?
Yeah, it does.
Cool. Now, the other major thing I wanted to talk about, and let's see if the book covers it before I spend time. Yes, it does. Okay. There's 2 more things that I should really hit on. The book doesn't cover resonance well, so I'll leave that alone a bit. Yeah. Okay. I'll have to do the next time. We'll have some more practice with thermal, as that's what the last quiz is on. So let me say that again. The last quiz is on thermal, so we'll have more practice on that Thursday. But remember that I said that my waves spread out such that the peaks stay 1 wavelength apart, right?
Okay.
Well, here's the thing. The speaker produces a constant power, a certain amount of energy each second, right? And we said that the waves, they carry energy, right? They're moving, okay? So how does that work with the wave actually spreading? It turns out that what happens is, as the wave spreads out, that energy gets spread thinner and thinner and thinner. You're already familiar with this idea if you look at ripples in water, right? What happens to the height of the ripple as it gets spread out?
It gets larger.
The ripple gets taller as it spreads out farther?
No.
What happens?
Kind of. I don't know really how to explain it.
It's smaller.
It gets smaller, right? Because that same constant amount of energy is spread across a larger area. It gets spread thinner. It gets basically spread so that the amplitude is smaller. Does this make sense? Well,
Yeah.
the energy per unit area, power per area, is something that we call intensity. Okay, we can talk about the intensity of this source at any given point, and we're going to measure it in decibels. But I see that I am out of time, so I'll have to pick up there next time. Okay, so one more time, let me say that the last quiz is over thermal. The last lab will be over waves, and we will pick up next time. Have a nice night, guys.
Thanks, David. Have a good night.
Thank you. Have a good night.
See ya.